Welcome to this lecture on nonlinear superresolution. So in this lecture we will cover stimulated emission depletion microscopy, nonlinear structured illumination microscopy, and pointillism. So that's what you see here. If you want a more general introduction into the topic, you might want to click on this link here or type it in, which will cover the basic concepts of superresolution, including Abbe's famous limit of resolution, and Fourier space and frequency space, which are somewhat important to superresolution. So let's jump right into the topic. Stimulated emission depletion microscopy, also called STED. So before we do so, I want to mention that, as you might know, there has been a Nobel Prize awarded in the year 2014 to William Murner, Stefan Hell, and Eric Betzig. Each of them contributed significantly to the development of superresolution microscopy, especially in the nonlinear and in the single molecule regime. So William Murner was the person to first see single molecules in a fluorescence microscope. Stefan Hell developed his famous stimulated emission depletion microscopy technique, and Eric Betzig is accredited for having developed the photoactivated localization microscopy, in other words, the single molecule imaging technique that allows you to localize all, millions of different molecules in a cell. We'll come to that later. This was a Nobel Prize in chemistry because the essential information in all of the three cases is really based on the molecular properties of the fluorophore in this case. So stimulated emission depletion microscopy. I'm showing this by a reasonably from the group of Stefan Hell. So Thomas Klar et al. Published this paper, and you see the basic concept quite nicely here. So basically, in a confocal microscope, you would typically have an illumination point spread function, which is sort of shown on the left here. So it's this green blob of light that you're basically scanning your sample with. Now, the thinking behind stimulated emission depletion microscopy is, instead of trying to directly improve the resolution, what about if we had some way to turn off the fluorescence of the molecule while the spot is scanning over it? So for example, if we could prevent fluorescence from this part when the excitation focus goes over it, and from this part, and ideally maybe even from this and this part, we are left with an effectively scanned area or volume that is a lot smaller, and this way we would then have a super resolution microscope that is essentially then not limited by diffraction. So the question is, of course, how would you achieve something like this? And the answer to that is you can deactivate a molecule by stimulated emission. So this is very much the same process that is used in lasers. So laser stands for light amplification by stimulated emission of radiation. And this is shown in this diagram here, which is a Jablonski diagram. So you have to basically read it as being the total energy of the molecule on the y-axis. And these are different molecular states. So this group of states here is called the singlet ground state. That means the electron is still in its resting cloud, so to say, in its ground configuration. However, if a photon comes in, a particle of light can excite it, the molecule, to this singlet excited state, which means that the electron or one of the electrons is in a different cloud. And at the same time, when you do that, due to the Franck-Contant principle, we automatically get into a vibrationally excited state typically. That means the molecule nuclei, they are vibrating. That will very quickly cool down within the range of a few picoseconds. And then we are in the vibrational resting state, but still in the singlet excited state. That means the electron cloud is still deformed and the nuclei have reached a new equilibrium position. And they have lost energy. So this is, therefore, we have a Stokes shift. That means the emitted light, by again going back to a vibrationally excited state, has significantly less energy as the excitation. And this is the typical process of fluorescence. So in other words, the Stokes shift with green excitation gives us red emission. So now the point of stimulated emission depletion is that we can somehow prevent the ordinary fluorescence by putting in a stimulated emission beam. So we can force this transition from happening to happen much more quickly than it would normally happen. And then again, if you pick a second, it decays to the ground state, vibrational ground state, and the whole process can begin from the start. So, well, as you see here, this sounds like we are stuck a little bit, because if you look at this diagram, how would we be able to actually tell the free emission apart from the stimulated emission? Because they seem to have the same properties here, and they typically do. However, the point is that the emission spectrum is rather wide and can cover a whole range of states here. And what typically is done is that the stimulated emission is done on the red edge of the spectrum. So that means the main part of the fluorescence would typically occur to one of these sort of lower levels at a slightly green shifted emission. And by the choice of very good filters, you can actually separate the scattering of the STED light, the stimulated emission light, and the stimulated emission itself from the spontaneous emission that happens mostly to one of the other states. So this way we have a way to separate the STED beam from the free emission beam. Okay, so now the second ingredient that's very important is that we can form a donut in such a way that actually the stimulated emission does not happen at all in the very center. And now what is really important to see is that this stimulated emission can be made arbitrarily strong, which drive this transition from the S1 state to the S0 state into saturation. What does that mean? Well, it means that we are actually causing stimulated emission pretty much everywhere around the molecule except that very position in the middle. So this is a conclusion that was reached by Stefan Hell as well as Stephen Baer and Oponin, I think is his name, with a Russian patent, so that you can actually with this trick of using stimulated emission and zero positions, you can cause a super resolution. You can get a super resolution microscope. So this is the process of stimulated emission is illustrated very nicely by a few slides that Kai Wicker made. What you see here is first the process of spontaneous emission. So you see typically a photon comes in, it leads to an excitation of the molecule, and then the molecule randomly somehow emits fluorescence. Well, of course, this fact that the emission goes in random directions, you have to not take too seriously. You can also think about a circular wave going out and it will being randomly measured somewhere. So this would be the process of spontaneous emission. And now, as opposed to this, in stimulated emission, it's a little bit different. And it's like this. So one photon comes in, you are excited, then a second photon comes by and sort of takes the excitation from the molecule away, and the emitted photon is sort of in the same state as the scattered photon actually. So that means the ordinary scattering from the excited molecule here would be indistinguishable from the stimulated emission. So that means when you measure one of these photons, later on you don't know anymore, was it scattered light or was it stimulated emission light? And you might have heard often that the state goes into the same as the de-exciting photon. And I'm not quite happy with this explanation, because that would pretend that your stimulated emission photon would somehow end up in the parallel wave if you're de-exciting it with a parallel wave, which I think doesn't describe this situation very well, because of course if this is a localized single atom or single molecule, the stimulated emission would still be sort of coming from this single molecule in a circular wave. But because it's amplitude and it's coherent with the wave, you will actually find it then mostly in the forward direction, but not only in a plane wave situation. So it really has to do with the scattering as well. If you want to go into this discussion, there's actually a nice recent a sort of online document by Andrew York that you might want to have a look at. Okay, so well, how do you make this donut? The trick is you are using, or you can be using, a phase mask. For example, such a phase mask that when you go once around, you're reaching a total delay of 2 pi in terms of relative phase, or if you talk in lambdas, then it's a 1 lambda delay when you go around. So what's the point of it? The point is that you can always find matching pairs of this back aperture. So you would put this in a back aperture or in the pupil plane of an objective lens, and that means that if one part of waves emit from here, another part from here, they have a relative phase shift of always pi. That means since you always find 2 pairs that destructively interfere, in total we get a 0 intensity in the very center of the nominal focal position. So rather than having the best possible intensity there, as you would normally do, you are intentionally actually deleting all the intensity there. However, if you then go a little bit sideways, it turns out that you get this very bright ring of excitation intensity around a very nice donut. And if you take care about the polarization in these things, which is typically circular polarization, you can actually make sure that even for high NA lenses, you get a true 0 intensity in the very center here. And so these donut phase mask, or sometimes I think called also TM01 beam, they can be ideal sort of beam shapes for stimulated emission microscopy, especially when it's about 2D imaging. There's other shapes that you might want to try for 3D imaging, because here you would actually get this 0 intensity along the optical axis, which then is not ideal because it gives you a very thin but very extended point spread function. So this is now a nice simulation that sort of shows you what's happening when you're increasing the intensity of the STED beam towards saturation. So imagine there's, like, on the left side, what is shown is the green excitation beam, or blue, it's shown here in blue as a section curve through the middle. And at the same time, I also show you in red the stimulated emission depletion beam. So, well, it is depleting fluorescence. So I have to think of it like this. If you scan the fluorophore along this line, what would you see? And if you're somewhere here, the idea is that if the red is strong enough, even though you might be, let's say you're here, you might be excited a little bit with that side lobe. Eventually, because of the very strong red stimulated emission, you would be causing stimulated emission, and therefore there would be no intensity left to be emitted from, or no excitation be left to be emitted from an excited molecule, because it is already caused to go down to the ground state, and therefore it cannot emit any longer the spontaneous emission. And as I said, you can separate spontaneous emission from stimulated emission, for example, by colors, so by selecting the right range of wavelengths. Of course, you can also use time signatures for separating them, or polarization signatures. But color is usually the most effective, and you're going to the red edge of the spectrum with the stimulated emission, making it slightly less effective, however, therefore easier to separate. You see here is now, if we have a very low amount of stimulated emission beam, then as you see that the emitted intensity shown in green here, so if you scanned the fluorophore through this thing, you would sort of measure the green curve, would follow pretty much still the excitation light. So there's almost no effect of stimulated emission. If you're now making that stronger, like here, you see that you're starting to squeeze down your point spread function. And now the trick is that if you interpret the red curve by going towards infinity, the probability of actually causing stimulated emission when you have been excited will go towards 1. So it will be a saturation curve that very quickly goes to 1, keeps constant more or less, and then if the 0 is very good, it dips to 0. That means there is still free emission possible in the center, and very quickly goes back to 1 as well. So this sort of saturation effect of the stimulated emission depletion is really the key aspect of the STED microscope. So what you see in this animation is that when we are driving the STED beam towards infinity, that our resolution becomes higher and higher and higher, and theoretically we can get infinite resolution this way. Of course, eventually we will be limited by other factors, for example, triplet state re-excitation, singlet state re-excitation, maybe overheating and so on. Also, photonic forces can start to drag organelles around and so on. So it's practically not always easy to get all the parameters right to get a good STED image. However, it is possible, and you will see now some nice results that show you how nice this can work. So this is an example, early example of STED images, 2005. And you see on the left side here some confocal data in XZ scan. And as you see, the resolution looks terrible. It's actually not so bad. It's just that the pixel size here is rather small. And that's pretty much all you can do with a good confocal microscope. However, with a stimulated emission microscope, and in this case, I think that was a combination with a 4Pi microscope, you can see that you can get very, very high resolution. The cover slip, which you see here, was coated with a fluorophore, so you can see this. You can think this is like a resolution test. You see about 53 nanometer resolution, and these, in this case, the microtubules have been stained with immunofluorescence, and you can see also that the resolution is really rather high. You can see these individual microtubules, and the resolution is in the range of somewhere, 53 nanometers. So this is a nice different example of even a biological application here. So what you can nicely see is the first image. It's barely possible to see the clusters that are in this membrane. However, this protein SNAP25, which I believe has to do with the endocytotic or exocytotic, I'm not sure, pathway of the cell, that it nicely comes in clusters. And when you have the STED image or even the deconvolved STED image, you can nicely see the individual clusters of these SNAP25 proteins. And on the right-hand side, there's an intermediate filament called vimentin, and you can also appreciate the very large gain in resolution between confocal imaging and STED imaging. Well, at first, this was difficult to get three-dimensional images, but then by using other types of beams, the Hell group actually was able to even do three-dimensional sections. And you see in this nice work here, the protein TOM20, which stains the mitochondria membrane, can also be optically sectioned. So you see here the hollow distribution of these mitochondria. And you can even have a 3D stack and visualize it like it's shown here. So this method is called ISOSTED because roughly it gives you an isotropic resolution. And if you are not dealing with biological images, but you're rather dealing with physical dyes, so to say, then you're sometimes not so limited by these re-excitation processes and so on. And this is shown here. So in this work, so-called diamond vacancies, nitrogen vacancies in a diamond are imaged, and you see that the confocal image is so bad, so to say, that you cannot resolve these individual nitrogen vacancy centers. In a STED microscope, you can actually see that quite nicely, and if you really drive it to the extreme, you can reach something like this. So this is a single nitrogen vacancy center image in a confocal microscope with a resolution of a couple of 100 nanometers here. Whereas the STED microscope can get you down to 8 nanometers in that publication. I believe there were other publications where they were even driving it towards 2 nanometers or something like this. So in this case, you can go to the extreme because essentially these nitrogen vacancy centers are almost unbleachable. When I first thought about it, the STED performances, I was thinking that it can never be really that fast. However, then there was a publication that showed that STED imaging can actually even do video rate imaging. And that really surprised me, and I want to show you how they've actually done that and why it was still possible, even though I first thought this cannot be done. So the reason there's several reasons for it. Well, of course, one reason is if you make a really small region of interest, you can scan it really fast. Maybe I should first actually motivate why I was thinking that you cannot do really fast imaging. Well, the reason is the original STED microscope is a single beam scanning microscope, and the fluorophore emits only a photon on average every, let's say, 1.5 nanoseconds or something like this. And that means if you want to be fast, you need to squeeze out lots of photons from lots of places. But because you're only probing a single point at a time, you can therefore not be very fast, because you need 1.5 nanoseconds to get out one photon. And let's say a good image, I thought, needs a signal to noise of something, let's say 10. So that means 100 photons you should be having for every position in your scan, and then you can calculate how long it takes you, and that makes it inherently slow. However, the trick here is, and basically the other effect is when you have a higher resolution, for example, a 2 times higher resolution in X, Y, and Z, you will need also 2 times higher sampling in X, Y, and Z. In total, that means 8 times more pixel compared to a low sampled image at low resolution. So doubling your resolution means 8 times more signal. If your signal to noise as measured on a single pixel is the same as before, I was thinking, well, you need 8 times more photons and 8 times more time, basically, to obtain the same image quality as you would get in your previous microscope. So it turned out that this thinking was not quite correct, because if you're imaging something which is very sparse, like single molecules, then you're actually fine with not having 8 times as many photons, but the same amount of photons. So if you imagine that you are looking at something that is only a few molecules in a lot of void area, then the image quality looks the same, having 0 everywhere and a few pixels with these molecules in them. And when you then zoom in, then you just have the same amount of bright pixels, or you just have more dark background. And in a way, that's the trick here that was used in this paper. So they are imaging single molecules within a bouton of a neuron at very high speed, because they scan a very small region. And this way they could demonstrate video rate 28 frames per second imaging of this. And if you post-process the data, as you can see here, they were able to show to even derive some properties about these molecules and so on. So very nice work to show that you can do STED imaging in video rate. So this was all I wanted to say at the moment about stimulated emission depletion microscopy. And now we come to the next topic, which is nonlinear structured illumination microscopy. So again, I want to stress, if you want to know the basics of structured illumination, I highly recommend you to watch these videos, either this one or this one, which is an introduction to generally super resolution microscopy, and the first one is on linear structured illumination microscopy. So as you might remember from linear structured illumination microscopy, which is this top part here, we had the following equation. In real space, we had the object density, i.e. the fluorophore density, being multiplied with our excitation pattern. The excitation pattern might be a sinusoidal or sine square wave, as it is shown here, and as it was shown in the last video. You see that this gives you 3 peaks in Fourier space, so a constant offset plus a sine actually of double frequency. And this characterizes the emission pattern. So if you look, this would be the situation in real space, sinusoidal or sine square excitation and this equation. However, in Fourier space, you will have this situation. The sine square gives you the 3 peaks, as I've shown, and then the object gets convolved with it, which means really that the objects get shifted to each of these delta-like positions, overlaid and added. So I just show one of these object components for clarity, but of course there's one attached here and one attached here, as described before. So now the trick is in nonlinear structured illumination that I realized eventually that you can have the following situation. If you somehow manage that the emission is not any longer linearly dependent on the excitation intensity, but rather follows a nonlinear dependence. So you have to somehow make it react non-linearly with respect to the light that comes in, or multilinearly if you have several factors that multiply together or something like this, for example, acousto-optical effect and stuff like this, or photochemical changes by another wavelengths and so on. And you can get nonlinear or multilinear effects. And if you have that, then this becomes an equation like this. And of course, then here you have to convolve with the Fourier transform of this nonlinear deformation. And this is shown here. So I termed this emittability because it tells you how well can something lead to emission when you are influencing your fluorophore in some way. And this emittability may then form a nonlinear dependence. And the interesting bit is that is of course not limited by optic anymore. So in optics, you can only get sort of sinusoidal waves at the top frequency here, but because this happens in photophysics or inside the sample, you are deforming it when it reacts, and therefore you're not limited to optics. And you see that what happens then is that you get these typical higher harmonics. So this is essentially what happens in an amplifier when you crank it up too much and you play an electric guitar. It might sound really harmonic at first, but then when you go to the nonlinear regime, you get the higher harmonics in there. And the same happens here in the spatial extent. And of course, to each of these higher harmonics, there's also information attached. So you might think that it's not possible to separate that information, but that is actually not true. Luckily, the shifting of this pattern means that you're having, so the Fourier shift theorem tells you if you're shifting in one space, the other one gets an e to the ik delta x. You're shifting by delta x e to the ik. And since this k is twice as much, 3 times as much, 4 times as much, and so on as the ground frequency, that means that the phase also sort of has harmonics, 2 phi. So if this is phi, this is 2 phi, 3 phi, and so on. That means all you have to do is you take a few more images than you would do in normal structured illumination. So you typically would take, for example, 3 images for structured illumination. However, now you need to take, well, 5, 7, 9 or so images. Actually, there are ways out of this dilemma as well, but you need to take more images to separate these components. And when they are separated, you can then sort of piece them back together. And even though the zero frequency isn't really seen anymore because the upper limit is indicated by these dashed lines here, you can still know where it is and shift it back to the right position. So if you're shifting this measurement such the zero coincides, it would end up somewhere here and you would get really, really high resolution information. And this game can theoretically played ad infinitum, and even with the slightest bit of nonlinearity, if it is a saturation effect, theoretically you get infinite resolution. However, it becomes practically very difficult to pull these very low signals out of the very high noise that's everywhere. So it becomes a question of signal to noise. So I think this is an important message in terms of resolution. Resolution is a matter of signal to noise ultimately. When you go to nonlinear structured illumination, and for all that matters actually also for stimulated emission depletion microscopy. So here you see some experiments that we've done around, when was it? Probably 2008, 2009 in King's College London. And this was some work done by Enno Oldevogel in my group there. And you see that we used a nice protein from the Nienhaus group, which is called IRIS-FP. It's a tetrameric molecule, and it's stained mitochondria. And you see here the wide field image. And in the next slide, you see the structured illumination reconstruction. That's what you get here. And now I'm going to show you what you get with nonlinear structured illumination, or what we got, which is this. And admittedly, it's not such a fantastic resolution improvement. However, if you look really closely, you will be able that you see much more details, for example, here. So it actually did increase the resolution maybe by another factor of 1.5. And we are currently still working on getting this into a live cell imaging method that is reliable, giving us something like 50 nanometer resolution. So there's also some really, really nice work by group, where Hesperigo has actually managed to get a 50 nanometer resolution, in this case on fixed nuclear pore complexes. So you see here the high resolution image compared to the best possible wide field TIRF image on the left side. So nonlinear structural illumination was able to get you the 50 nanometer resolution, which was precisely what was sort of expected in my first publication on 2002 on this topic of nonlinear structural illumination. And actually, lifestyle imaging has also been achieved in a similar range of resolution in the group of Eric Betzik. So what you see here is some actin filaments and some new structures that were found there. So they had this fantastic science paper in 2015 showing you structured illumination or nonlinear structured illumination.